Hello everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering the probability mass function, the tool we use to describe probability distributions for discrete random variables. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's going to build his first real probability distribution, not a guess about the odds, but an actual function with a formula. And with it, he's going to try and figure out where he's been losing money the most consistently while gambling. He opens up another one of those mysterious letters. We established in the previous video that discrete random variables take on countable values. The probability mass function is the tool that assigns a probability to each one of those values. The probability mass function, or PMF, of a discrete random variable x is the function p of x equals the probability that x equals lowercase x. For each specific value that x, the random variable, can take on, the probability of x tells you the probability that x lands exactly there. Every valid probability mass function has to satisfy two conditions. First, every probability has to be non-negative. Probability of x is greater than or equal to 0 for all of x. There is no such thing as a negative probability. Second, when you add up the probabilities across all the possible values, you end up with exactly 1. The probabilities must sum to 1 because the complete set of possible values covers every outcome that could possibly occur. These two conditions are not just formalities. They actually mirror the probability axioms that we started this whole module with. Non-negativity is axiom 1, summing to 1 is just normalization. The entire sample space has a probability of 1, and the probability mass function is how we distribute that probability across the possible values. It helps to have a concrete sense of what a probability mass function actually looks like before diving into the main example. Take a simpler case first. Suppose that you hold a bond that is rated BBB today. Next year, it could be rated anywhere from AAA down to default. Each possible next year rating is a possible value of the random variable. The PMF assigns a probability to each one, based on historical transition data. The probability of staying BBB is about 87%. The probability of moving up to A is about 6%. The probability of downgrading to BB is about 0.05, and so on. Each of those numbers is a value of the probability mass function. You can verify the distribution is valid by checking non-negativity. All entries are positive, and checking that the sum across all the possible values of next year's ratings equals 1. This PMF then answers questions you actually care about. What is the probability of downgrading to junk, defined as BB or worse? You can add the probabilities for BB, B, CCC, and default. That ends up being around 6.8% for a typical BBB bond. What is the probability of an upgrade? You can add the probabilities for A, AA, and AAA. What is the probability of no rating change at all? You just read off the single entry for BBB. We often want to visually represent a probability mass function. When we do this, we often plot the possible values on the horizontal axis and the probabilities as vertical bars. You get a bar chart of the distribution, and the height of each bar is the probability of that value. All the bars will sum up to 1, and you can quickly figure out things like what's the most likely outcome by figuring out what the tallest bar is. The shape will tell you where the probability mass is concentrated and how to spread it out. The phrase probability mass function is intentional. For a discrete distribution, probability is literally concentrated at specific points. The PMF tells you how much mass sits at each point. This is the conceptual counterpart to the continuous case, where probability is spread across intervals rather than concentrated at points, and we will get into that in the next video. Danny puts down the letter. Danny has been playing 10-hand sessions at the poker table for years. He has a rough sense of his win rate based on how things actually go, but not how he would like them to go, and he puts it at about 40% per hand. He builds out the probability mass function. With a 40% win rate per hand and 10 hands in a session, the number of winning hands x follows a binomial distribution. The probability of winning exactly k hands is the probability that x equals k. We can actually use the formula for a binomial distribution to compute this outcome. He works through the calculations. Winning 0 hands has a probability of roughly 0.006, 1 hand 0.04, 2 hands 0.121, and so on. He plots the distribution. The probability mass is clustered around 3 to 5 hands. He has been telling himself that finishing a session with 2 or fewer hands is a bad run, a fluke that happens maybe 15% of the time. The distribution says that the probability of 2 or fewer wins is 0.006 plus 0.04 plus 0.121, which equals around 0.167, roughly one session in six. He does not lose most sessions, but a 1 in 6 win rate is not a fluke. He has been calling a predictable recurring outcome a fluke for years. So that is the probability mass function. For a discrete random variable, the PMF assigns a specific probability to each possible value. It has to be non-negative everywhere and sum to 1. You compute interval probabilities by adding the values in the range, and you use the complement rule when working with tails. The probability mass function is the complete description of a discrete distribution. Everything you want to know about the probabilities can be figured out from that function.